Good morning. Okay, so let's start the class. So before we talk about the materials, so let me briefly tell about this announcement. So, so this Wednesday we will have our tutorial. This will be about the pigeonhole principle and also the counting. So yeah, if you have not started checking the assignment, yeah, please do so in these 2 days. And then next Monday we will have our quiz. So the quiz will be about these 2 topics, the pigeonhole principle and also the counting. And then yeah, so I am sorry that I will be away from Taiwan this week. So if you have any question, yeah, please. Okay, so the best option is to find Simon or Keke or Jiaxin. Okay, and then so to find the tutors. Just in case the time does not match, you may send me emails and I will try to answer you while at my earliest possible time. Is that okay? Okay, good. Okay, so today we will talk about something easy first, and then something very difficult. Okay, so the easy thing is to prove identities involving sets. So this is what we are going to talk about, proving set identities. Okay, so last time we have talked about some set identities like what? Like the commutative laws, the complementation laws, the distributive laws, associative laws, etc., etc. So we have talked about a lot of laws. So these are identities that we can prove. And there can be other identities that we can prove. So today we are going to talk about this thing. So the first method, so there are going to be 3 different methods we want to introduce. The first one is called the membership table. And you will see that this is going to be very similar to the truth table we have talked about before. So truth table is to show 2 logical propositions. They are logically equivalent. And here, a membership table is to show that 2 sets, they are equivalent. So let's do this first. Okay, this is going to be very easy. Okay, so suppose that this is the identity that we want to show. We want to show that A intersect B, if you do the complement, so this is something that is not inside this A intersect B. So if you draw a Venn diagram, this is A, this is B, this part is A intersect B, and then the complements of A intersect B will be all this yellow area. Is that okay? As long as it is not inside this A intersect B, we should include this. And then this is equivalent. We want to show that this is equivalent to the complements of A union the complements of B. Okay, so this is a particular case of the De Morgan's law. Okay, so to complement A intersect B, you complement A, change this from intersect to union, and change this to complements of B. So we get this. Okay, so this is De Morgan's law. And how we can show? Okay, the idea is to show that whenever something is here, it will be here. And whenever some element is not here, some item is not inside here, it will not be inside here. Okay? Okay, so the method is very similar to a truth table. So we write down A here, B here, A intersect B, A intersect B, the complement, and then not complements of A, complements of B, and then this complements of A, union complement of B. Okay, so we are going to write down this. Okay, so if you look at a particular item, there are 4 different cases that we can think about. Either this item is in both A and B, or this item is in just A but not in B, or this item is not in A but in B, or this item is not in A and not in B. Okay, so there are 4 different cases. So let's think about an item that is in A and in B. And is that okay? And then see what will happen. So let me write down the 4 different cases. So an item could be in A but not in B, not in A but in B, and not in A, not in B. Is that okay? Okay, now if an item is in A and in B, then it will be in A and B. So this is the tick. Is that okay? Does that make sense? Okay. If it is a tick here, then it must be a cross here. Okay? And now, how about this one? This is complement of A. So if it is a tick here, then this is a cross here. If it is a tick here, then this is a cross here. And cross, 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 union, cross. If it is not in A and it is not in B, then it is not in A union B, so it is a cross. So far, if you understand what I'm doing so far, could you please raise your hand? Okay, excellent. Okay, so let's complete the other. So let's do this more quickly. So this is intersection. So we get a tick only if both of them are ticks. So in all these 3 cases, they are all cross. Okay? And this is the complement of this one. If it is cross here, then it will be a tick here. So we get 3 ticks here. Is that okay? Okay? Now here, not, this is like not. Okay, this is the complement of A. So it is tick, tick, cross, cross. So you get cross, cross, tick, tick. And for B, it is tick, cross, tick, cross. So you got cross, tick, cross, tick. Is that okay? And for this union, union is whenever there is a tick here, then we should be a tick. Okay, so we get tick, tick, tick. And now, once we have completed this membership table, so this table is to check for any item, if it is a member of this one and this one, will it be a member of this one, will it be a member of this one, and so on and so forth. And after we have computed this one, we focus on this column. This column is about what happens in A intersects B complement. And also this column is in not A union not B. And we find that they agree. They agree. So it means that no matter what item that you look at, whenever it is not in the left-hand side, not in A intersect B complement, then it is not here. Whenever it is in here, then it is in here. So what does it mean? It means that these 2 sets has to be the same. Okay, an item is here, then it is there. An item is not here, then it is not there. Okay, so they are equivalent. Is that okay? So this is exactly the same idea as using a truth table. Okay, good. How about 2? Okay. So we have a method 2. Okay. So the other part is we want to show that 2 sets are the same. So another way is we want to show that each set is a subset of the other one. Is that okay? So the other case is each set is a subset of the other. So the reason here is that if we can show that X is a subset of Y, and then Y is a subset of X, if we can show that this is true and this is true, then this will imply that the X set must be equal to the set Y. So this is the logic behind. Okay? The same idea. It means that all the things that appear in X appears in Y. On the other hand, all the things appears in Y will appear in X. So that means that the two sets has to be the same. It contains the same items. Okay? So I have an example. So let's use the same example there. So we want to show that. So this is the target. We want to show A intersect B, the complement, is equivalent to, so it is the same set as A union B, no matter which A and which B you talk about. Okay, so the proof, okay, so we want to prove this. So we show that this is a subset of this one, and this is also a subset of this one. So if we can show both, then done. Okay. Okay, so we first show what? A intersect B is a subset of A union B. Okay. So here, so what does it mean? Okay, we want to show that this is a subset of this one. That means that any element or any item here must appear here. Okay, this is meant by subset. Everything that appears on the left-hand side, it will automatically appear in the right-hand side. Is that okay? So we are going to do this as, so for any element, let's call it X, that is an element of A intersect B. We want to have a lot of arguments, and then we hope to get, okay, for every X in A and B, we want to show that after some logical deductions, we will have X is an element of A union B. If we can do so, then we can show this part. Is that okay? So this is the target, and then we need to fill in the content here. If you understand what I'm talking about so far, could you please raise your hand? Okay, excellent. So we don't know how to fill it yet, okay? But let's fill it a little bit later. We will do so. But on the other hand, this is not the complete proof. For this one, we just show that this is a subset of this one. Is that okay? So what we need to do is we also need to show the other part. We want to show that this one, the right-hand side, is also a subset of this left-hand side. And then for this one, we want to show something similar. For any Y, that is an element of A union B, after some logical deductions, we will have a conclusion that Y is in A intersect B complement. Okay. If we can show this and show this as well, then we show that the two sets are equivalent. Okay? Okay, now let's fill in the things here. For X, so let's fill in the details. So if I tell you that X is in A intersect B complement, then that means that X is not in A intersect B. Does that make sense? Okay. Now, if X is not in X intersect B, then what do we have? What do we have? X is not in A. X is, well, then what is? So if you use logical thing, so it is saying that this is true, not X in A and B. Is that okay? So x in A and B will be false, so not x in A and B will be true. Is that okay? Is that okay? Strange, yeah. Okay? So if we have this one, this implies what? This implies not of what? X in A and B, it means that x in A and, so notice that this is not a union or not an intersection. This is the logical AND. So x is in A intersect B if and only if x is in A and x is in B. Is that okay? Does that make sense? Okay, so just one last step. The last step is not this one and this one. We can use De Morgan's law. This time we use De Morgan's law. We get, okay, so we have another so. If we have this one, so we will have another one. So not x in A or not x in B will be true. Okay? Yeah, I'm running out of then so I use so again so. So what does it mean? Not x in A, not x, so x is not in, not x in A, not x in A. Not x in A, so x is in, not x in A, x is not in A. So x, okay, yeah, just make it longer. Okay, x is not in A or x is not in B. Okay, and that's so. So x is in not A or, this is or, x is in not B. Okay, so finally we get, let me borrow some space here. So finally, so x, if x is in this one or in this one, then x must be in not A union not B. This is what we want. Is that okay? So this is somehow lengthy, very lengthy, but this is, you are proving this by using logical deductions. So this works. So this is just a simple example. And in this example, we are showing very simple thing. We just involve two sets. So when there are only 2 or 3 sets that are involved, then it is better to use the membership table because it doesn't take a lot of time. And here, it is easy to make a mistake here. Okay, but on the other hand, if you have many symbols, many sets that are involved, then it is usually better to write down a proof like this. Okay, so this is the first part. So let's, for an exercise, let's do the other part. So let's see what will it be. Yeah, to do the right-hand side, it will be great if we can check whether this left-hand side proof works in the reverse direction. If it works, then done. Okay. So first of all, if y is in not A or not B, then what does it mean? It means that y is in not A or y is in not B, right? Yeah, this works, right? Now, if y is in not A and not B, then, so we also know that y is not in A or y is not in B. Yeah, so this also works. Okay. Now this work. So let's check. Okay, so we also have the next one. It also works. So we have not y in A or not y in B. Okay, it works. And then we also have the De Morgan's law, but this time, yeah, we take the negation outside and then negate everything inside. So we will still have negation of what? This one, this one. So we have y is in A and y is in B. Yeah, this works. So we will have what? So we will have the negation of y is in A intersect B. And finally, we will have the conclusion that y must be in not A intersect B. That's it. Okay. Okay. So for this time, it's lucky, and it is usually, so we will usually be lucky. So when these two things are really equivalent, all the steps that you are doing here usually are reversible. So x is in this one if and only if x is not in A and B. And x is not in A and B if and only if not of x is in A and B is true, and so on and so forth. Actually, every statement here occurs if and only if. So if you get for any x is in A intercept B negation, the complement of this one, it happens if and only if. So what you get in the conclusion is if and only if x is in not A or x is in not B. So you get the proof. Is that okay? So usually you can save half the space by mentioning that actually for each step here it is happening if and only if, and then you get a simpler proof. And this is the second way that you can prove that two sets are identical. Okay? And of course there is a third one. The third one is apply known set identities. Apply the laws that we have, or the known identities. Okay, so this one I will just give you an example. So this is going to be simple. Okay, so here, let's say we want to show, okay, this is the question, prove that. Prove that what? Prove that A union B intersect C. So I have a bracket here. This one is equivalent to C union B negation intersect A negation. Okay? Okay? Okay, so we try to prove. So this is our proof. So you may start from any side, maybe the left-hand side to the right-hand side, or the right-hand side to the left-hand side, or the left-hand side to some intermediate part, the right-hand side to some intermediate part, and they are all equivalent to each other. So let's start from the left-hand side. You have A union B intersect C, and then the negation, right? The complement. Okay, if you look something like this, then the best is to use De Morgan's law, right? To try to simplify this. So you don't want to have a negation of a lot of things. So you want to have the negation of any simple thing. So you take this negation, the complement, so you get A intersect bracket B union C. Is that okay? So this is by De Morgan's law. Okay, so it is not just by De Morgan's law one time, many times. We are applying De Morgan's law many times. Yeah, if you just apply De Morgan's law, you just have not A or complement of A intersect the complement of B intersect C. But we will need to have De Morgan's law again on this part so that this becomes the complement of B union the complement of C. Is that okay? Okay, but anyway, this is De Morgan's law and De Morgan's law. We have this one. And okay, then this is easy. So this will be equal to or equivalent to, you just switch the direction of these two, switch the order of these two. So what is the reason that we get this one to this one? We are swapping what? The order of n. So this is called what? You check it, so this is called the commutative. So we commutative. So the commutative law. So this looks pretty much the same as this one. Okay, and then we have one more set. So this is C union B intersect not A. And what is it again? So this is again commutative law. Okay, so this is the commutative law on this symbol, and this is the commutative law on this symbol, on this operation. And that's it. So, okay. Okay, good. Okay, so this finishes the discussion on proving set identities. So this is about the simple, easy thing today. Okay, now we move on to something difficult, really difficult.